Um, am I audible?
Yes, you're audible.
Okay, all right. Okay, so let's get this started.
Should we
So
wait for
right
people
now,
to comment?
yeah, what? I you can hear me, right?
Wait for people to comment.
Yeah, what? I Tejas, can you mute it? Yeah, yeah. Hold on.
There is distortion in your
Tejas,
side.
can you mute it? Yeah. Okay, we'll just wait a little more for people to join.
Hi, am I audible right now?
Yeah, you are you.
Is there echo?
No, no, no. It's
Hi,
fine.
am I audible?
Okay, guys. So let's start today's SDG session called TrueSight by CodeChef-VIT. So before we go into it, I would just like to give a brief introduction about why we did it. So basically, SDG Sustainable Development Goals are a collection of 17 global objectives established by the United Nations in 2015 as part of the 2013 Agenda for Sustainable Development, which is quite the hype now. These goals like aim to address a broad range, like you can see all the 17 ones. They are pretty interconnected regarding global challenges, including a lot of different stuff that needs addressing. So for our project, the solution that we wanted to bring was based on SDG 16, which is peace, justice, and strong institutions. It basically, the goal there is to promote peaceful and inclusive societies for sustainable development, provide access to justice for all, and build effective, accountable, and inclusive institutions at all levels. So, basically, the overview we had towards the solution, we took inspiration from one of the Smart India Hackathon 2024 problem statements where we participated. The problem statement is basically a bit about the development of AIML based solution for detection of face swap based deepfake videos. So our problem statement revolves around how deepfakes have become increasingly sophisticated, making them difficult to distinguish from authentic videos. This has actually led to a lot of serious problems in sectors like media, politics, and law enforcement. It's basically everywhere. So there was this one time where a manipulated video of US House Speaker Nancy Pelosi was widely circulated on social media, which was edited to make her appear drunk. Or when the Russian-Ukraine war, a video of the Ukrainian president had surfaced where he appeared to tell his soldiers to surrender. Well, the manual detection of deepfakes is both time consuming and error prone, whereas the existing deepfake detection tools often fall short when it comes to detecting more sophisticated face swap manipulations or are targeted towards large organizations, leading individuals and smaller platforms with limited access. which is why the solution that we decided to propose is TrueSight. It's an AI ML solution that provides a robust answer to this challenge by providing a multidimensional analysis covering both visual and auditory cues, real time scalability through cloud based infrastructure, and accessibility to both individual users and large enterprises via a similar interface or API. So, if I want to give you a technical overview, TrueSight utilizes multiple advanced algorithms to detect deepfakes by analyzing the consistency between lip movements and audio and focusing on texture and style discrepancies in images. So, basically, we trained our model to detect like two formats. So, one is the video, and the other is MP3 format. So, it can detect deepfake audios as well as videos, which is very necessary in the current world. By, as I said, as I mentioned, video we use lip movement, audio we focus on discrepancies and all of that. So coming to our development phases, so the first one, as you can see, we had 7 development phases. The first one was data collection. So as you know, if you have ever worked on a building a ML model or anything, in order to train the model you need data sets, right? So we had to collect deepfake videos or images from publicly available data sets. We used face forensics plus plus, celebdf, and deepfake detection challenge. Other than that, we had to also balance the data set with real videos and images for model training to maintain the balance, and also of course ensure diversity in data so that it just has a good balance of age, gender, ethnicity, resolution, and all that. Coming to our second phase, it was basically data pre-processing. So, we had to resize and normalize images or videos for consistent input dimensions. We had to also extract frames from videos if working with frame-based deepfake detection, which is what our problem statement revolved around. And if you're familiar with it, we also had to apply data augmentation techniques to improve the model generalization and remove low quality or corrupted samples from the data set. Um, and then we came to feature extraction. We leveraged a lot of pre-trained models like, for example, VGG19 or just ResNet to extract their meaningful visual features. Including, we had to include the frequency domain analysis to detect artifacts commonly present in deepfakes. Also, we had to use, handcrafted features like, facial landmarks, eye blinking patterns, which are actually very important when you need to detect a deepfake video. We'll go into depth. My teammate Akshat will go into depth in it later. Basically, all of that were pretty relevant. Coming after, so after we were done collecting the data and all that, we were like, when you're very close to the model development, we came like we had to build a classification model using architectures like CNN, Capsule Network, or vision transformers. We'll also go in depth to that and experiment with ensemble techniques combining multiple models. That's one of the plus points of our project. It uses like it has an ensemble of multiple models. It also has to to incorporate attention mechanisms to focus on subtle artifacts in a deepfake content. And coming to our next phase, we had to train the model on a balanced data sheet of real and fake samples. And we also had to perform hyperparameter tuning to improve model performance and use techniques like cross validation to avoid overfitting. We were the one of the final phases is evaluation and deployment, where we basically evaluate the model using matrix like accuracy and precision, test the model on unseen deepfake datasets to validate generalization, compare the model's performance against existing benchmark solutions that are already there in the net, from which we took inspiration from. And we also had to integrate the model into a web app. That's what we went ahead with. Like we had the difference between web app and mobile app. So we went with ahead with a web app. And it also enable users to upload videos, images. Can you just give me 1 minute? Yeah. uh, yeah. Coming back to deployment, we also had to enable users to, like, that's how the website works. We'll also show you the implementation. We had to enable users to upload videos or images and get real-time deepfake detection results. One of the points that also stands out with our model is that so basically it's like you can say whether a video or a audio is fake or not, but what we focused on is, okay, why is it a fake video, okay, or why is it not a fake video. We have included multiple graphs to like show a proper analysis on why it was detected as fake or not. We also added like the explainability features that I just mentioned, and just they just highlight the suspicious regions in detected content. um, Coming to our tech stack, so as you can see, our solution is built using AI frameworks like TensorFlow, PyTorch, and OpenCV. These technologies ensure that the models can be trained efficiently, so that they can handle large data sets and so that they can operate in real time. Like the model branching architecture that I mentioned about allows us to basically process videos in parallel, making TrueSight capable of real high speed detection without compromising accuracy. So now I would like my teammate Akshat to just go ahead with the explanation of the rest of the models.
Hello, am I audible?
Yeah, you.
Let me present my screen. Hello.
Yes, Akshat, you're audible. We can see your
Okay,
screen.
yeah.
Go ahead. Yeah.
So good evening to one and all present here. I am Akshat Rajkumar, and I will be explaining in detail about the various AI models that we used in our project TrueSight. So coming to the first model, which is the LipNet. LipNet, as the name suggests, it basically performs end-to-end lip reading. So, and this is one of the most important models which helps in deepfake detection. LipNet, the overview of LipNet is that it takes the input video and it does lip reading based on the what the person is speaking in the video, and then compares it with the actual audio which is taken as the input, and see if they both are matching. Of course, if they are matching, then it's a real video, and if it's not matching, then it's considered to be a deepfake. So this model has been trained for over 30 hours. Now jumping into the details or the architecture of this particular model, the input are the video frames. So the input video and the audio, especially the video part, the in the pre-processing part, we split the video into different video frames, and each frame is considered as an image, which is passed as the input to this particular model. Second part is the dlib lip extractor. Dlib is a specialized library that helps in detecting the important features of our face. For example, let's say eyes, nose, cheeks, ears, etc. And for this particular model, we will be extracting the lip region, as our main focus is to do lip reading. Now, after extracting the lip region, we will jump into the block one. As you can see, it consists of several layers such as zero padding 3D, convolution 3D, activation, batch norm, etc. To give you an overview of what this thing does, let me show you a small example. So how a convolution layer works is, it takes a filter. As you can see, there's a 3x3 matrix, and this is considered to be a filter, and it performs a process called as convolution. Let's take the image on the left to be the input. It basically does a matrix multiplication and passes through the entire image, and after doing this matrix multiplication, the output will is seen on the right side. Now this filter is called as a vertical filter. So what it does, it highlights the vertical or the straight lines in the image. As you can see on the right side image, you can see that the straight lines or the vertical lines are highlighted much more than the curved lines. And this is how an AI model actually understands the different characteristics that is present in the image. And after passing through a couple of convolution layers, it will basically look somewhat like the image on the left, as you can see, of the cat. For we can take the input image to be the cat, which is on the right side, and this image can be of a very high pixel. Let's say, for example, it can be for 1024 cross 1024 pixel image. Now, after passing through several convolution layers, it somewhat becomes like the image which is on the left side. The pixel dimension of this particular image might be less than 200 or even lesser. But as you can see, the important features of the original image has been captured or preserved even on the left image, although the pixel has been reduced exponentially. Although the output image is not very clear, we are still able to somewhat make out that it's a cat, and this is how convolution layers actually work, and how AI models understand pictures. Now, moving on, after the passing through this block one, it goes to a time distributed layer. Time distributed layer is basically a pre-processing technique for the next block, which is the block two, which is BiGRU. The full form of BiGRU is bidirectional gated recurrent unit. So what this layer does is it takes the frame of a video frame, and then takes the video frames which are the futuristic video frames and the previous video frames as the input in order to predict what is going on in the current frame. So to give you a clear example, let's take this particular image. As you can see, this is just a video and it's been split into various frames. Let's take the first row for example, and let's name from the left side. We'll start naming it as frame 1, 2, 3, 4, 5, and 6. And for, let's say, for the model is now currently processing the frame 3. Now what the bidirectional GRU layer does is it takes the frame 4, 5, and 6 as the futuristic frames as the input, as the futuristic input, and also the frame 1 and 2 as the input, in order to detect what is actually going on in the current frame, which is the frame 3. In our context, as we mainly focus on lip reading, so the futuristic frames and the previous frames are taken as input in order to detect what letter or what word the person is trying to speak in that particular frame, and this gives us a random set of characters or words, and there's a specific function called as a specific loss that is called as a CTC loss, which I'm not going to go into details. But basically what it does is it combines this random words and gives a proper meaningful word which is actually spoken in that particular video, which is detected through lip reading. And this lip the what the AI model detects is basically purely based on lip reading, and with zero involvement of the audio. After that, we compare the audio and the lip reading, predicted lip reading words, and if they match, of course it's not a deepfake, and if it doesn't match, we output it as a deepfake. This is the first model. Now moving on to the second model, which is called as a MesoNet. So this architecture basically helps in detecting deepfakes by focusing on the mesoscopic features. Mesoscopic features include, we can say it includes the facial expressions. For example, when a person speaks, a normal person speaks, there'll be a slight movement in the cheek muscles, slight twitching of the eyebrows, although not very visible. It is of course present, but with deepfakes, all this is missing. So this a particular model makes sure it captures or it notices this such kind of small details, and finally helps in identifying if it's a deepfake or not. Now moving on to the third model, this is a gaze tracker. Although a very simple model, this is one of the most efficient and useful models for detecting deepfakes. The problem with the deepfakes is that the eye movements are very regular. They are not smooth like normal humans. The pixel value, when the deepfake video blinks, or the people in the deepfake video try to blink, the pixels are scattered all over the place, which makes the blinking look irregular. Sometimes there is no blinking at all, or the blinking intervals are very irregular, which helps in identifying deepfakes. If you see the process of how this model is built, is that explained in model 1, it takes video frames as input, and it does eye landmark detection, which is basically using DLib module as mentioned before, and instead of taking the lips, this time we focus on the eyes. And then using this, we calculate something called as the EAR ratio, or the eye aspect ratio, which helps in detecting if the person is blinking or not. To give a little more context to this EAR ratio, it can be defined as the vertical distance, as you can see in the image, the vertical distance divided by the horizontal distance between the eyes. So once this ER, when we blink, when our eye is closed, the ER ratio is reduced, or the value is reduced, and when it falls below a certain threshold, we can tell that the person is blinking. This helps us to detect blinking, and also helps in analyzing the smoothness of the blinking. Let's say the irregular intervals or regular intervals in the blinking, and helps detecting deepfakes. So these three models which I've covered help in detecting the video part of the deepfake. We also have another model which helps in detecting if the given audio is a deepfake or not. Moving on to that particular model, which and yeah, so this one is an example of how our eye tracker actually looks like, or gaze tracker model. Moving on to the deepfake audio detection, we do this mainly using something called as the MFCC, or the mel frequency substitute coefficients. So what this includes is basically it's a combination of various mathematical formulas which helps in detecting if a given audio is a deepfake or not. So step one is basically pre-emphasis, which passes a high pass filter in order to reduce the noise in the given input audio. Next step is framing. So basically, this audio, just like the video, are split into short frames, usually between 20 to 40 ms, and each of these frames is analyzed independently in order to detect if it's a deepfake or not, to notice all the details in each frame. Then we apply something called as the fast Fourier transform. I think if you are focused in your differential class, you might have come across this name. We basically apply Fourier transform in to this particular frames, which gives us a different kind of number. Basically, all these frames can be converted into numbers, and applying Fourier transform gives a different set of numbers, which helps in detecting if it's a deepfake or not. And then coming to the Mel filter bank, which is the step four. So humans can actually the perceives frequency on something called as a Mel scale, and all the processes, pre-processing step done in this particular MFCC is to convert the given audio into something similar to what a human ear could hear. So this particular model just tries to imitate or replicate a human ear, which helps in detecting deepfakes. This is also this so basically this melt filter bank is done using triangular filters, something similar to the convolution layer but a bit different. Next, then we do a normalization process by applying the logarithm on the mel filter spectrum. This helps in reducing the wide range of the speech signals. And then on top of the fast Fourier transform, we apply something called as the DCT, or the discrete cosine transform, another mathematical formula which I'm not going to deep dive into. And finally, after applying the DCT, it will give us something called as the MFCC coefficients, and this basically structures the input audio into a graph, and this graph or the spectral shape of this graph helps in finally achieving the what we need, whether to detect if it's a deep fake or not. These are all the major models which I've used in this particular project. I would like to pass it on to my friend Tejaswa, who will show the not live demo. He'll show you the demo, and he'll explain each steps in that particular demo.
Hi everyone, my name is Tejaswa Pandey, and I'm going to explain how our website actually works. So let me present my screen. Mm, So we have used React for the front end part, and we have used rapid API for connecting our backend to the model. Uh, let me show you our website. I have already started it from the code, and here it is the live model of it. Like so, we made it very user friendly. So if someone comes to our website, it will be very easy for them to use our website and to understand what is going on the website. Like as you can see, we have like given tips how you can be productive and how the things will work. As you can simply click to get started, and uh, you can simply click to get started, and you will be redirected to the uploading page. In this website, the demo I'm showing you is not actually the thing, but and I will show you the actual demo what we have made, because here it was a little prototype type, but at the end of the thing, we were managed to integrate backend and front end, and we were able to upload the video part and audio part also. So here, as I can upload the video part, and it will be previewing your video, and we can upload it right here. But it will take time, so I will be showing you the demo how the website works. So this is our actual website, which we worked on, and it's fully integrated with backend, and it takes responses from the ML model Akshat told you about and explained you properly. It will use Rapid API to take the request from the client side. Client side is browser or the user, which will take the inputs from the user, and it will reflect back the responses from the Rapid API. Like this is the landing page of the website, and as you can see, obviously the design has changed, as I told you about. That was not our final product, and here we are. I'm showing you the part of the ML model which will be working on the video part, as we will be uploading a video which is basically intentionally AI based. So that it can detect or not, it will not detect to see that it is detected or not. We will be uploading a video, and you can see the result. Like it's a AI developed video. We are going to upload it, and it will be going to the backend through Rapid API, and then we will be getting our responses from the backend, and we will be showing you the results like metadata, micro expression analysis, gaze tracer, frequency analysis, and behind these data, we have also explained what these data actually conclude. Like you can see the micro expressions appear unnatural, suggesting that this is a deepfake. Or as from the gaze tracer model, as Akshat told you, it is concluding that the blinking pattern is irregular, indicating that this is likely not a deepfake. And it also tells you about the video duration, the resolution of the video you have uploaded, the frequency analysis, and uh, speech detection. We also see that what could have been the actual words that were spoken in the video, and what they are actually speaking. We compare them, and after comparing them, we will conclude that rather the video is AI detected or not. So like that video we uploaded, we have this conclusion that no speech detected for synchronization analysis. As we can see, there was no lip syncing in the actual audio and the audio in the video. So we will give the final conclusion that is this is a defect. And for the audio part, I will show you. We will go back to the upload page, and we will be uploading an audio. And wait, like we will be uploading an audio, and it will check whether the audio is a deepfake or not. As you can see, the model is working very fast, because it's a very lightweight audio, and like obviously it will take processing and all. I'm not representing the actual model because it will take time. We have fast forwarded the video to for the ease of the showing you how our model is working. And through the after uploading the audio, we will be getting results like metadata, the format of the audio, the audio data, the audio MEI spectrogram, audio MFCC, and like obviously the final conclusion for the audio we have uploaded, that this input audio is classified as deepfake. Now I will ask Monami to further explain how how will we will be scaling the product, and how will we taking it like a business.
Before that, I will just like to take a couple of questions if the viewers have any. Okay, 1 minute. Just give me a minute. I'll just share my screen quickly because 1 minute. So basically about if we come to scalability, yes, we did think about that, like basically our scalability and future plans, if you might say so. TrueSight's cloud-based infrastructure ensures it is highly scalable. Our solution can handle increasing user demand and pretty large volumes of data, and offering real-time detection, as you just saw that they just showed you. The modular architecture of the model also allows us and gives us a lot of space for future upgrades to handle new deepfake techniques as they emerge. Coming to future scope, what we can expand on is legal and forensic application, a user-friendly mobile app, as I showed you in the very beginning, we talked about it, or just real-time deepfake detection, which we can do with if we collaborate with streaming services like YouTube or Instagram. It can be something like as you're just swiping, like Instagram has a lot of fake content nowadays. So if we can just build something real time, something that like detects deep fakes real time, like as you're scrolling or as you're watching a video, that actually controls the spread of fake news. So that's with the scalability and the future scopes. If you all have any other questions, what are the main concerns regarding it? Okay, so like deepfake has recently increased a lot. Like it's before it was not a problem at all when social media emerged and all. But the rise of generative adversary networks, also known as GANs, they're basically the backbone of modern deepfake generation. Progressive GANs and style GANs, they're capable of generating hyper realistic faces which can fool even experts. So there's this website called This Person Does Not Exist. Yes, there's a website named that. And it can basically generate entirely synthetic yet realistic human faces. Other than that, if we come to AI driven voice and motion manipulation, deepfake technology is actually no longer limited to just face swaps, at least not in this time. So advanced models can be used to manipulate voice, which is why we cover two aspects. We cover the deepfake video detection as well as audio detection. So basically, when it comes to voice, tools like Descript and there's another called Resemble AI, they can clone someone's voice with just a few seconds of audio. I don't know if you all have heard it, but a lot of scams have been carried out in this way. Even body movements, actually, there are models like first order motion model. They are capable of replicating body gestures onto other individuals. So these techniques are increasingly integrated into multimodal deepfakes, the face, voice, and gestures. So yeah, that was about the concerns. Next question. Why then OpenAI was having difficulty in designing a model which caches plagiarism, that whether an assignment is copied from ChatGPT or not. I've heard this happen. You are absolutely not wrong. This has happened, and while we are considering we did this as a part of a hackathon, so we only covered audio and video because they are like the most sought after
Yeah,
deepfake.
so the problem about this is, look, the concept of Gen AI, or basically the Gen AI, is relatively new, and it's growing at a very exponential rate. But although Gen AI is growing at that exponential rate, the major problem it faces is catching these deepfakes or plagiarism. So that is not at par with the Gen AI. So that's the major reason why the OpenAI is not able to design a model which is to detect if the assignment is copied from GPT. So that was the major, the motivation for us to build this kind of a deepfake technology. Although our idea was focused around video and audio, the plagiarism is also a very important aspect, which we did not, wasn't the major focus for this, but also which we might include in the future aspects for it. Yeah, yeah. So
Yeah,
that's
but
the
like
reason.
actually, ChatGPT generates text that mimics human writing styles a lot. If I'm not wrong, like it's very difficult to differentiate from manually written contents. Like it does not have any obvious
There are a
fingerprints.
few models which do help
Yeah,
in catching plagiarism, but
yeah. We
I
just
just
didn't
told you
expand on
it's not
that
at par with
part.
the actual Gen AI, which is currently going.
Yeah, exactly. Hope that answered your question. Is that all? That's it. We can like okay. Wait. Okay, so someone just asks what are the limitations of current deepfake detection tools. So actually, if you go on like the current limitations, what basically when we check them out and we were focusing on like what the current ones lack, they are basically a lot of them actually are unable to detect audio visual synchronization issues because there are many tools that focus solely on the visual aspect of deepfakes. Number one, and like the in order fail to analyze audiovisual inconsistencies. My bad. There's also like it also like of course has high computational requirements. Like defect detection tools often require substantial computational power, like high end GPUs and all that. And the current ones, the thing is, as I just mentioned, which was a threat, that the emergence of GANs, it basically the default generation techniques are evolving very rapidly, so producing more realistic and subtle manipulations, like coping with them becomes a bit difficult. You need to have a model which is like constantly developing. And also like many deepfake detection tools are black box systems that provide a prediction without explaining why or how a video was flagged as fake, which is why it becomes not really trustworthy. So which is why we focused on that aspect a lot.
Yeah, I would
Wait.
also like to include to this
Yeah.
question that so the current tools which are available in the market, they usually focus only on one perspective. They don't look at the different perspectives. Let's say like how our model covered the different perspective, like audio, video synchronicity, and then eye tracking, etc. Usually, the most of the tools detect only one perspective. Either it's only eye tracking or it's only video and synchronicity. So that's one of the major limitations of current deepfake detection tools.
Okay, so I guess that answered your question. um okay, so if there are no further questions, I guess we'll wrap the session up. I will quick, just give me a moment. In case there are like no other questions, this is the attendance. We are just sharing QR code for the attendance form. We are still open to questions if anybody else has any. Till then, we'll just keep the attendance form displayed.
So one more question popped up. I think it's how well does it work if the key facial features are obstructed in the video? So I would like to answer this question. Yeah, as I mentioned before, our model looks at various perspectives and not only one perspective. So let's say the key facial features are obstructed. Um, let's say the eyes are not clear or something like that. So in that case, our other models will take over. Let's say the audio video in synchronicity, which will mainly focus on the mouth. And let's say if the mouth is not very clear, then then our gaze tracker will take over and look at the eyes, look at the eyes, and then of course there are other models. So this is how basically we mainly solve this by looking at the other perspectives. If one perspective is blocked, then you look at the other POVs. Any more questions?
I guess we'll just give a bit time for the EXC students to fill out the form. All right. So I guess that's the end. Thank you for attending the session SDG TrueSight by Coach of VIT.
Bye.
Thank you for your time, guys.